Good morning, class, and welcome to this beautiful Sunday morning. I hope most of us have gone to church. Some are still preparing to go. Some are back already, you know. Now, sorry for those in communication will say the breaking transmission or communication. We are trying to prepare the lecture modules in such a way that it will be easy for you to understand. So we're going to look at 4.1. Remember, we looked at module 3, kinetics, first order, zero order, second order reactions, and so on. And even influence of temperature on chemical reaction, that is Arrhenius equation. And I hope you've gone through that and you're able to understand. So now we're going to electrochemistry and redox reactions. We're starting with module 1, that is module 4.1, Introduction to Electrochemistry and Redox Reactions. I still remain Professor Engineer J.C. Igwe. By the outline, we're going to be looking at introduction, some definitions, some units and more definitions. Why do we study electrochemistry? So we're going to look at why we study electrochemistry, and then we'll conclude. Now, this introduction will go in form of a little trace of the development or history of electrochemistry, just a summary of it for us to understand that a lot of people have been working on this concept so many years ago to get to where we are right now. Until the end of the 18th century, the study of electrochemistry was concerned by what we know and refer to as static electricity. That is, electrochemical phenomena at high potential and intermittent current. The beginning of the study of electricity of low potential and steady current and the start of electrochemistry may be traced to observations of Galvani and Volta. Galvani in 1791 observed that a frog's muzzle twitched when touched by an iron and mercury wire in contact. These and similar phenomena were described as animal electricity or galvanism. So you can imagine Galvani was running an experiment, look at the time, how many years back? 1791. And, unknowingly put together iron and mercury wire while they were connected to a frog's muzzle. And, the muzzle began to shake. Now that means just like maybe a human being that has fluid, blood running inside the person, you now go and touch a high tension wire that there is current in it. That is electrocution. So the example of what happened to that, the frog's muzzle was a kind of electrocution. So Galvani now decided to look at it. What exactly is happening to this frog's muzzle? And that was described as animal electricity. Something that you have not seen before, so or also called galvanism. Now it was after that Volta constructed a voltaic pile, and that is what we can call the forerunner of all electrochemical cells. And he used that to now run experiments to confirm that galvanism is also true. Now that voltaic pile was the first source of large current or low potentials. Now further to that, Nicholson in 1800 used that pile again to pass current through water to obtain hydrogen and oxygen at the electrodes, which was the first example of electrolysis. Of course, we're going to see, I think it should be in module 4.6, electrolysis, what electrolysis actually means. Now, we're going to the man who can be said to be the father of electricity, Faraday. He now used solutions of fused salts to confirm these, what Nicholson did, splitting water into hydrogen and oxygen. So Faraday went further to do some work on that. Now, but at that stage, there were so many things that were not clear. For instance, electricity was regarded as one or two fluids, so people didn't know exactly what was happening. There was no agreement whether chemical reaction was there and so on. So all these things, as time went on, are things that experiments were beginning to make a little clear. Now, one of the important landmarks was the theory of Grotius. Grotius in 1805, tried to look at mechanism of electrolysis, where he now explained why the products of electrolysis, appear only at the electrode, which we are going to see. Now, he envisaged a positive and negative portion of the molecules. You see how this thing is coming out, gradually, positive and negative, when we start talking about cations and anions. But at this stage, nobody knew what was positive or the name of the positive and negative. Grotius was only envisaging that there must be a negative portion and a positive portion of the molecules, which now exchange patterns on the action of the electric field. Now, it should be noted that at this time, laws of chemical combinations were the only experimental evidence in support of the concept of atoms and molecules. So it wasn't clear what was actually going on. So it was not until the end of the 19th century that this concept gained universal acceptance. Now, following this universal acceptance, many similar theories were, widely accepted. Now, at no time was it conceived that independent charged or even independent dissociated uncharged fragments or molecules existed in solution. So nobody knew, for instance, that if you dissolve something like sulfuric acid, H2SO4, that it is possible that SO4 2 minus, ion can exist in solution on its own. Now, the next era was dominated by Faraday. Remember I said if anybody was to be called the father of electrochemistry, it was Faraday. So he now brought in a lot of clarifications in all these things that have been happening. And that's why we have some of the definitions now, anode and cathode. Now, he regarded these as the positive and negative ends of the solution following Grotius. Remember, Grotius was envisaging that there should be a positive and negative end. He wasn't sure. Now, Faraday now regarded that as that which, following what Grotius and assume alternate throughout the solution. So you now see that it's becoming clearer that we can differentiate between positive ions and negative ions. So at the same time, we can also differentiate between positive electrodes and negative electrodes. We now apply the name cathode to the negative electrode and anode to the positive electrode, where reduction and oxidation takes place respectively. We also have electrolytes, substances which can be decomposed by electric current. That's why, for instance, the blood in our system is an example of an electrolyte. And that's why it's easy for somebody to get electrocuted. Once you have a connection to a high voltage, then that blood, the fluid in the body, can be decomposed. That is dissociation. It's just like trying to fragment them into positive and negative ends. And that will cause the cells to, break down. And then they say the person, has been electrocuted. So an electrolyte, substances which can be decomposed by electric current. There are so many of them. I've just given you an example of the living, the one in the living cell. Copper sulfate can be an electrolyte. Zinc sulfate, an electrolyte, as we are going to see further. Many of them. Now we have anion and cation. This is where the acronym of the Students' Chemical Society came from. Those in chemistry, they will now come and shout, great anions, great cations. This is where it's coming from. And these are the parts of the electrolyte which go to the anode and cathode respectively. Remember we said the anode is a positive end, whereas the cathode is, whereas the cathode is the negative end of the electrodes. Now we're now coming here now to say anion and cation. So you can now see that positive will go to negative, whereas negative will not go to positive. That is, the positive ions will go to negative electrodes, whereas the negative ions will go to positive electrodes. And that's why you have oxidation and reduction taking place. So when oxidation is taking place, reduction is taking place, and we shall see, that's why we call this redox reaction, reduction, oxidation reaction. Therefore, we can define electrochemistry as a study of the production of electrical energy, or the study of production of electricity from energy released during spontaneous chemical reaction. So you can see, when there is spontaneous chemical reaction, energy will be released, which is in form of this electricity. That's why if you put a bulb to that, you see the bulb will be, shining, because that spontaneous chemical reaction will produce electricity. That is the flow of electrons. Electrons coming from the anode going to the cathode, in the external circuit. Of course, we are going to see that later. So spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. So you can see there are two types. One of this part of electrochemistry is the electrochemical cells we are going to see, spontaneous. The other part is the electrolytic cells we are going to see, that is by electrolysis. Now, some unit and more definitions. You remember this is an introductory part, so that when we meet some of these things later, we'll be able to know what they are. We can define energy. Energy is measured in joule, and joule is equal to coulomb multiplied by volt. Power, current is measured in amperes, which is charge per unit time. That is the unit of coulombs per second. Power is measured in watts. That is, power is equal to work per unit time, which is also current times potential, which is measured in volts and amperes. That's volt multiplied by amperes. Remember, amperes is current. Now, electrical potential is given by energy per unit charge, represented by V, sometimes by E, capital E. The fifth one, electrochemical work, is therefore equal to potential multiplied by current multiplied by time. And that is charge multiplied by potential. Remember, current times time is equal to charge. So where E is electrical potential in volts. We also have that for 1 mole of electron, the charge is Q. And that charge Q is equal to N subscript A multiplied by E, where N subscript A is the Avogadro's number. So Avogadro's number multiplied by the charge of an electron. And this value is equal to 96500. That is 96,500. And we will see what we call this. In fact, number 7 tells us that this 96500 is called F, that is after Faraday. 1 Faraday is equal to 96500 coulombs. Now, all these things we are looking at, why do we even study electrochemistry? Look at the batteries we have. Say every battery is an electrochemical cell. And indeed, a measure of its voltage is Gibbs free energy indicator. Batteries, our watch batteries, your phone batteries, touch batteries, there are different kinds of electrochemical cells. And as you know, even as a layman, if you're not doing sciences, you know that there are some of the batteries you can recharge, There are some of them you cannot recharge. There are some of them, once they are no longer working, you throw them away. Some you can recharge, like your phone batteries. As you keep recharging, it gets to a point where you can no longer recharge. The battery power has gone down. Again, in nerve impulse, in biological system, there are electrochemical potentials. If you remember our biology, we're not going to do biology here, but we want to give an example. If you remember nerve impulse, what is nerve impulse? A very good example, if I pinch you, for you to know that it is painful, or somebody has pinched you, or you have marched on a nail or bottle, there will be transmission of nerve impulse to the central nervous system, where the analysis will take place and now give you, an input, an output system. The output will now let you know that something is wrong, it's painful. That's why such reactions also vary from human to human. There's somebody you pinch now, it takes the person a fraction of seconds to know that you have pinched him or her, but there's somebody you pinch now, it takes, longer time. So this nerve impulse also takes place as a result of electrochemical potentials between our sodium, potassium ions, exchange of ions along the line. Again, concentration gradients across cell and other cell membranes cause electrochemical potential differences. For example, in cell membrane transportation, filtration, let's take something like, our kidney, the glomerulus. That is where the filtration takes place in the kidney, the kidney tubules and glomerulus, filtration. I don't want to take you, I know those in biological sciences, but if you go and just, browse, you see this. The differences in electrochemical potentials can result to some certain transport mechanism, active transport, facilitated transport, and the rest of them. Again, in manufacturing and industrial productions, for example, the process used in the manufacture of electron beam mass used in television tubes, electrochemical reactions. You can see that. What is the basic electrochemical process in photosynthesis where carbon is fixed in living matter? Now, if you go to photosynthesis, you have the light reaction and the dark reaction. Photochemistry is also there. That is electrochemical process. How does hemoglobin transport oxygen in blood? And what are the oxidation states of iron in the process? Remember that iron is there. In fact, iron is the major constituent that forms the complex for hemoglobin. If you look at the structure of hemoglobin, you'll see iron there. Now, it is the same, electrochemistry or electrochemical reactions, electrochemical potentials that can cause the picking up of oxygen, to transport to the blood cells, picking up carbon dioxide, removal of carbon dioxide. So you can see that there are so many reasons why we can say the study of electrochemistry is important. So that's why it is important for us to know the basics. For you at this elementary level, we're not going to go deep. We're just going to look at the basics of electrochemistry. We've come to the conclusion of this module. We've looked at some definitions in electrochemical reactions. We also looked at some units in electrochemistry. And then, of course, we explained why we study electrochemistry. Of course, basically, remember, we tried to trace the history of electrochemistry. Just simplify the history. We didn't go so deep to start, mentioning all the names, bringing up all the pictures. We're just trying to make this video to be as short as possible so that you will be able to enjoy the video. Thank you so very much. I expect to see you in the next class. Thank you.